Hi everyone, so we continue with lecture 7 where we're going to talk about mass balance on multiple units. So the learning outcomes from this lecture, at the end of this class you should be able to perform both non-reactive and reactive mass balance on multiple units. In this case without recycle yet. Next week we will continue with recycle, bypass and purge. Okay, so why do we have to have multiple units? Well, by now you should know that it is very hard to do all of the tasks below with only one equipment. It's impossible for a chemical plant to accomplish all of these tasks using just one multi-purpose equipment. To heat, to cool, you need heat exchanger. To purify, you need a separator, separation equipment. To react, of course, you need reactor. Separate phases, again, it's a separation equipment. And then to modify the shape or sizes, you need a special equipment for that. So chemical plants often need some to all of these key steps. For example, to purify raw materials before entering the reactor, to adjust the phase, i.e. whether it's liquid or vapor phase at the right temperature and at the right pressure, mix it to the right concentration before finally entering the reactor. And then after the reaction is taking place, the product from the reactor outlet you need to separate or purify. And let's say if there are some unreacted reactant that can be recycled back into the reactor, maybe we need to adjust a bit the phase and the temperature and also the pressure maybe. Okay. Alright, so before you finally package or store your chemical product, you may need to adjust the concentration. If it's a solid product, you may want to adjust the shape and sizes. Let's say you're producing urea as a fertilizer, so you want it to be in uniform shape and size. So each of these steps here require many pieces of equipment, not necessarily just one equipment to do everything here. So what are the challenges with multiple units? So with different unit, different function and different designs, you have various inlet and outlets, and you need to know which streams should be connected to which equipment. Okay, for example, in this problem here, suspended solids in the reactant is filtered away before the stream enters the reactor. So you know that the suspended solids in the reactant must go through filter and then only enters the reactor. But is this block diagram enough here? So you have to think. So it's not. So you have to have a the filter needs to have an additional outlet, not just one outlet. Yeah, so to filter out whatever is not wanted before entering the reactor. Okay, so you need to know how many streams involved and what would be in the stream here and what would be in the stream here. So let's go through first example. A stream containing water, methanol and dissolved oxygen is fed into a distillation column. The top stream of the distillation column is partially condensed to enable oxygen to escape. Okay, the condensed liquid is the methanol water azeotrope. Okay, just simply mean it's just a methanol water mixture. Part of it is returned to the column and the rest is withdrawn as the distillate. Part of the bottom liquid stream of the column, i.e. the distillation column, is reboiled into vapor and returned to the bottom of the column. The remaining bottom stream is taken off, containing mostly water. So first step before we actually do the material balance on multiple units, you need to be able to just draw the block diagram of a given problem correctly. Okay, so I would like you to just pause this video for a while and try to draw the block diagram based on this description. Okay, let's compare your answer with mine. Let's see how much similarity do we have. So let's draw a distillation column since the feed is fed to a stream is fed to a distillation column. So this is your distillation column. So the feed to the distillation column contains water and methanol and some dissolved oxygen. And then the top product of the distillation column is fed to a partial condenser. Okay, so maybe you should know that the top of the distillation column is normally it's vapor. Then because of its a partial condenser in this question, so some of it will become vapor and some is liquid, meaning not all of the vapor will be condensed into liquid because it's only a partial condenser. Okay, so it also says that part of the liquid is being returned back to the column and some is being withdrawn as a distillate product. Okay, so what happens to the liquid product at the bottom of the column? So this is liquid. It is being fed to a partial reboiler. So where some of the liquid is reboiled, become vapor and being fed to the column again, and some of the liquid fed to the reboiler remain as liquid, and this is a liquid product from the bottom of the column, contains mostly water. Okay, so the distillate here will be containing mostly methanol, and most probably the dissolved oxygen will not be dissolved anymore and maybe escape in the vapor phase. So this is just additional information to make sense of what the process was talking about. Right, next going on to example 2. In a continuous process, liquid X is vaporized before being mixed with hot air. The combined stream is then compressed to 5 bar gauge before entering the reactor. The reactor effluent is flashed off to 1 bar gauge in a flash drum to form a vapor and a liquid stream. The vapor stream is sent to an absorber to remove CO2. The liquid stream is pumped to a distillation tower where the product Y appears as a 99.5 mole % distillate and the unreacted X comes out as the bottom stream at 90 mole % strength. So sketch the diagram again. Let's take a pause for a few minutes for you to attempt drawing the plot diagram on your own and then compare with my answer. You have to pause the video yourself, yeah? Okay, let's compare with my answer, hopefully. Okay, this liquid X, is sent to some heat exchanger because it needs to be vaporized before. So this is vapor X, then being mixed with some hot air. So the combined stream is being compressed. Assume this is a compressor. Okay, and then being fed to a reactor. This reactor. So the outlet of the reactor effluent is fed to a flash drum. So what is the flash drum? You can try to Google it. So basically, flash drum is an equipment, a separation equipment. Let's say if here you have a mixture of vapor and liquid entering the flash drum. So the output of the flash drum, maybe here is vapor. Top here is vapor, and down here is the liquid. Okay. It manipulates the temperature and pressure to separate the mixture into vapor and liquid phases. So the vapor will have different composition of component X and Y, and then liquid also have different composition depending on the relative volatility. So the question said that the vapor stream from the flash drum is what is being fed to a absorber. So you can draw an absorption tower or absorber. So normally the gas stream will go from down bottom of the absorber. And to remove what? To remove CO2. So the vapor here will be containing less CO2, because the idea is that maybe the vapor here contains high amount of CO2 and you need to meet some specification or requirement that it must exit with less amount of CO2. So the absorber will release the vapor with less CO2, but absorber also needs something, meaning a liquid solvent. It doesn't say in the question, but you should know based on lecture 3 overview of unit operation. So absorption tower or a scrubber or a stripper, you need 2 inlet and 2 outlet, 1 gas, 1 liquid. 2 gas and 2 liquid. So this liquid outlet is containing the solvent plus some absorbed CO2. Okay. So what happens to the liquid outlet, liquid product from the flash drum? It says that it's being fed to a distillation column. So you can just draw a distillation column. I'm sure your drawing is better than mine because I'm using this tablet. So this distillation column, the top product is containing 99.5% by mole of Y, and the bottom product contain 90% by mole of X. Okay, this is just a practice on how to translate the description from words into a figure, block diagram. Any question, please WhatsApp me in the group. Okay, next is DOF analysis on multiple units. So why do we need to do DOF analysis on multiple units? Before this, in a single unit reactive or non-reactive material balance, you already did DOF analysis just to ascertain whether the problem can be solved, or just to confirm whether the problem can be solved. But in a multiple unit material balance, you need to do a DOF analysis to determine where do you want to start first. Okay, so there are two major approaches in doing DOF analysis for multiple unit material balance. One is based on control volume. Okay, control volume. This is a straightforward approach. So you find the number of variables and number of independent equation of the streams crossing the control volume only. Alright, crossing the control volume only. You don't care about the other streams that does not concern the control volume. Okay, so for example, let's look at this block diagram where you have a reactor and a separator. Okay, you have a different control volume. The red box here can be one control volume. The separator can be another control volume, or you can have a bigger control volume as shown in the green dashed line here. So these are all possible control volume. So if you want to solve a problem, you start from the control volume or CV where the DOF is equal to 0. So that will make your life easier. So what you do is, if you have a reactor, choose a reactor as the control volume. So you only concern yourself with the streams crossing the reactor. If you have a look at the separator as your control volume, so you only look at the streams crossing this box. But if you look at the the process as a whole, the big green box there, then you concern yourself with all the streams crossing the box. In the middle here, you don't care, because you only look at the control volume crossing, the streams crossing the control volume. Okay. Another method number 2, approach number 2 is based on the inspection of all streams. when the above fails, because sometimes you cannot find a control volume where the DOF equal to 0. So if this doesn't work, then you go to the second method. So based on the inspection of all streams, so let's say you have this process here, reactor and separator as shown in this slide. So instead of looking at the control volume, you just have a look, you count how many number of variables you have in the whole flow sheet and how many independent equations are given in the question. Okay, an aqueous solution of Y. Okay, this one already being described. The question has described. You can read the question. So the question here is, you want to find, of course, the goal of material balance is you want to find out the flow rates and the composition of every compound and in every stream in the given question. So now you want to find E1, X4, X5, R1, X1, X2, X3, and R2. Right, so you have to know which control volume works, which one you want to start with first. So you either have stage 1, or you can start with stage 2, or you can also have a look at the whole process, combining stage 1 and stage 2. So let's go through one by one options for the control volume. So option 1 for the control volume is, let's have a look at the stage 1 first. So when you look at the control volume stage 1, you only concern yourself with the streams crossing stage 1. So if you look here, you can do a DOF analysis, count all the number of unknown variables. So it says here that the number of unknown variables is 8, but I always like to just clarify what are the 8 unknown variables. So I start with R1, X1, X2, X3, then E1, and then X4, X5, and then R2. Sorry, this is number 4. Okay, so you have 8 unknown variables. Next, how many equations do you have? So it says here you have 3 species balance, which are for Y, W, and S, and 2 sums of mass fraction. So what does it mean is that this x1 plus x2 plus x3 equals to 1, and also x4 plus 0.65 plus x5 equal to 1. So these are your independent equations. So then in total you have 5 independent equations. So then let me erase my writing first. Then your DOF is 8 minus 5 greater than 0. So you may not want to start solving your question from this control volume. You don't want to start here. Next, we look at the second option for control volume, which is stage number 2. So for stage number 2, you only concern yourself with the streams crossing stage number 2. You don't care whatever is happening with the stage 1. So looking only at the stage number 2, you can also do a DOF analysis here. So total number of unknown variables here is 4. You can just list down what are those: E1, X4, X5, and R2. Okay, then the number of independent equation, 3 species balance, which are for one for Y, W, and S respectively, and 1 sum of mass fraction. So you need to know that the sum of mass fraction here should be 1. This will give you another independent equation. So looks like you have a DOF equals to 0 here, since you have 4 minus 4 equals to 0, right? You may want to start here, or you may want to see another option for control volume, and if possible we want to avoid simultaneous equation, because as far as possible we would want our life to be much easier. So let's have a look at the third option for the CV, which is the whole system, which is you combine stages 1 and 2, and you don't care what is happening in the middle of the process. You only look at the whole input and output. So combining stages 1 and 2, the input are this stream, the feed stream, and the solvent stream, and the output are these E2 and R1 stream. So you can do a DOF analysis also. Here we have 4 unknown, which are R1, X1, X2, X3. And then you have 3 species balance, YWS, and 1 sum of mass fraction. So this one equal to 1. So the DOF looks like 0 here. So you can start either at the whole system or at the stage 2, up to you. But from here, you can obtain R1 quickly. If you see here from the overall balance, from the overall balance here, input equals to output. Because this is a non-reactive system, yeah, you can assume input equals to output. 100 plus 150 equal to output is 15 for E2 plus R1. So you can quickly calculate what is R1 here. So you get 235 kilogram per second. So you have solved for R1 already. So you can solve for X1, X2, X3 quickly. So usually for non-reactive material balance, the whole system is usually the simplest. Remember this for non-reactive material balance. Okay, now that you got R1 equals to 235, let's try to solve for the remaining unknown variables x1, x2, and x3 using the control volume where we combine stages 1 and 2. So just now R1 is 235 kilogram per second. So we do a balance on component Y. So 0.2 times 100 at the input equals to x1 R1 plus 0.5 times 15. So 20 equals to 235 x1 plus 7.5. So from here you will get x1 equals to 0.053. Next you can do a balance on W. 0.8 times 100 at the inlet equal to 0.45 times 15 plus 235 times x2. Solve for x2, you will get 0.312, or you can also just write to 0.31 if you want to keep it to 2 significant figures. To find x3, you can either use a balance on S, or an easier way is, because you already know x1 plus x2 plus x3 equals to 1. So x3 is 1 minus x1 minus x2. Put in numbers, you will get 0.635. If you use x2 is this, or you can round it up to 0.64. So now you've got R1, X1, and X2 and X3 for the outlet of stage 1, one of the outlet stream of stage 1. You can work on getting E1, X4, and X5. Okay, now that you got the values from R1, X1, X2, and X3, you can work on getting the remaining unknown variables. Once the variable are found, let's move on to another control volume. Okay. Okay, now you want to find E1, X4, X5, and R2. So what you can do is, you can either use stage 1 or stage 2. So let me solve it using stage 1, and you are highly encouraged to do using stage 2 as your own initiative. Okay, using stage 1 as CV, the control volume. So the overall volume overall balance is 100 plus R2 equals to R1 plus E1. So you can put the known values 235 plus E1. So R2 is 135 plus E1. Okay, then you can do a balance on component Y, 0.20 times 100 plus 0.07 R2 equals to x1 R1 plus x4 E1. Simplify the equation. 0.07 R2 equals to, since you have found x1 and R1, you can just plug in the numbers. 0.053 times 235 plus x4 E1. Then you simplify the equation. Okay. And then you can also continue with doing the balance on W. 0.8 times 100 plus 0.20 R2 equal to x2 R1 plus 0.65 E1. And this is 80 plus 0.2 235 times 0.31 plus 0.65 E1. Simplify, you get 0.20 R2 equals to 0.65 E1 minus 7.15. So you can label this is equation 1, this is equation 2, and equation 3. So what I see from here, I think it's easier to use equation 1 and equation 3 to solve for E1 and then get R2 and then get the x4. Okay, can you do that? Of course, you can do that. So using equations 1 and 3, oops, red color, then you can use 0.2 and then replace the R2 with 135 plus E1 equals to 0.65 E1 minus 7.15. Then you can solve for E1. I don't need to go into the details of this. From my calculation, I get 76 kilogram per second, but some of you may get 75 depending on the rounding up of the numbers you got before. So I got E1 equals to 76 kg per second. Then I can get R2 because R2 is essentially 135 minus E1, oh no, plus E1. So 135 plus 76 is 211 kilogram per second. Then from that I can use equation 2 to get x4. So from equation 2 it's 20 plus 0.07 R2 equals to 12.455 plus E1 x4. So replace with the known variables, known values, 211 equals to 12.455 plus 76 x4. Now you find x4 equal to 0.29. Then finally you want to find x5. So you can use the summation of mole fraction equals to 1. So x4 plus 0.65 plus x5 equals to 1, then x5 shall be 0.06. Okay, check your answers with mine. Check my answers too. Okay, so those are um, the steps on how to solve for the unknowns using control volumes. Okay, you analyze one by one the control volume. You find out which control volume you want to start first, where the DOF equals to 0. Let's say you want to use the second approach, i.e. you analyze the whole flow sheet to do the DOF analysis and to determine whether you have enough information to solve the problem or not. So this is the same problem given to you in the example 3 just now, the same numbers, everything. It's just that we're going to show you a different approach on doing the DOF analysis. So from here, what you do is you just have a look at the entire flow sheet, all streams, you calculate the number of unknown variables. So here you have 8. So you can find out what are the 8 unknown variables: R1, X1, X2, X3, E1, X4, X5, R2, and those are your 8 unknown variables. So the number of independent equation, you have two sum of mass fractions, so this is equal to 1. These are the other sum of mass fraction here. Okay, so these are the two sum of mass fraction, and then you have 3 species balance on stage 1. Okay, in stage 1 you have 3 species balance, and also in stage 2 you have another 3 species balance. So in total you have 8 independent equations. So your DOF is 0. Okay, continue with a nasty case. You know, why is it a nasty case in this example? So FYI, this example, this nasty example, is actually the same problem as you have been given in example 3, only that in this example now we change the where the unknown and unknown variables are, such that you won't get a DOF equal to 0 in any of the control volumes. So that's why it is called nasty. Otherwise, it's just a normal problem anyway. Okay, so if in this case DOF is not equal to 0 in any CV, it's always more than 0. If you don't believe me, try it yourself. Okay, so what you do is, if you see there is no control volume where the DOF equal to 0, but the system is solvable when analyzed using the alternative approach. What is the alternative approach? The alternative approach is when you analyze the stream by stream. You still see that we have 8 unknown equation, and we have 8 unknown variables, and 8 independent equation. We have this sum of mass fraction equals to 1 here, sum of mass fraction equals to 1, so that gives us 2 independent equations. And also we have 3 species balance in stage 1 and 3 species balance in stage 2. So in total, 3 plus 3 plus 1 plus 1 equals to 8. So it is solvable. It's just that you cannot use any of the DOF in any of this control volume where the DOF equals to 0. You have to just try to solve it simultaneously. Okay, so these are the answers for both of the example, the nasty case and the original example 3. You should get the same answer. So just to take note that for E1 I got 76, and for R2 I got 211. So there's some discrepancy somewhere because of the here in this one, it should be 0.312 or 0.635 if it's not being rounded up to two significant figures. So in general, I'm still accepting answers close to the actual answers if the calculations are correct, if the method is correct. So you are highly encouraged to try example 3 on your own. although you have seen me working out the answers step by step, but please just close the video and try solving it on your own. Then you will know whether you understand it or not. And if you got stuck at any time, you can just repeat the whole video again. Okay? Okay, moving on to the last example, example 4. So this example is a system with reaction, okay, reactive system. So for the following reactor separator system, given 25% excess B was fed and that the outlet streams of the separator contains 40% of N, determine the conversion of A in the reactor. So given all this information, so the given information is that in the one inlet stream you have 80% mole of A, and then the balance is inert, and then in the other stream of the reactor you only have B as the feed. And these are the information. A plus B produces 2P, and then here you will have A, B, P, and also N. And at the separator, all of the product P will appear in this stream, and the remaining products A, B, and N will appear in another stream. So you are asked to determine the conversion of A in the reactor. So first, of course, we need to do a DOF analysis. Before that, we need to select a basis. So we select a basis of 100 kilomole per hour of feed stream of A. Because why? The question only gives us the composition of this stream. And then they only ask us to find out what is the conversion of A. So whenever you are asked to find the conversion, the composition, the molar flow rate doesn't matter, and if it's not given, you need to assume a basis. And if you assume a basis, if you already assume a basis of 100 kilomole per hour of feed stream, then let this be the only basis that you choose. Don't put the other assumption, or you cannot put 100 kilomole here, 100 kilomole output, you cannot. Okay, if you already say 100 kilomole per hour at the input, at the feed stream of this, then so be it. That's the only basis. So if you put that as the basis for the other stream, the other feed stream to the reactor, where only B is in there and 25% in excess of B, so this one you label as an unknown, N1. Let's say N1. And then what? You label the reactor outlet. You know that the reactor outlet shall contain unreacted amount of A, unreacted amount of B, and then the product P and the inert. Whatever being fed to the reactor for the inert will go out of the reactor. And then the separator. The question already gives you that all of the P will be in this stream. So whatever being fed to the separator for P will come out here. And what appears at this stream, the other stream here, is A, B, and N. So how you write down whatever you label at the reactor outlet, that is the amount that will come out in this separator. So do a DOF analysis at the reactor to see where we want to start first. So let's say our control volume is the reactor. We have two unknown variables, which are N1 and XA, and we have only one independent equation, which is the 25% excess B. So DOF is equal to 1. Separator, we have two unknown variables, same like reactor, N1 and XA. And at the separator, we are only given that the composition of N at this stream is 40%, or in mole fraction 0.4. So DOF is equal to 1. So if you look at the overall, here overall means it's not the overall control volume. This is using an alternative approach. Okay, you just look at the overall stream approach for DOF analysis. So you look at the whole stream, all of the stream, all you see are two unknown variables, which are N1 and XA. And for the whole problems, all you have are two independent equations. One is 25% excess B and 40% N in this separator outlet stream. So make use of this information to find out N1 and XA. So given here already the answer XA is equal to approximately 0.94. So I would like you to pause and to try solving the question before looking at what I'm going to share with you the solution. So, assuming you have paused and attempted the question yourself, let me share with you my solution. So I think from this in this case, it's easier to start with finding N1 because N1 is 25% excess B. You know, from the reaction A plus B produces 2P. So 1 mole of A requires only 1 mole of B. So in this case, using a 100 kilomole per hour of basis, your input is 80 kilomole of A per hour. So N1 would be 1.25 times 80, which is 100 kilomole per hour of B being fed to the reactor. Then we want to find XA. So looking at the separator outlet, this stream where you have A, B, and N. So you label it in terms of kilomole per hour. So for A is 80 times 1 minus XA. So for B is N1 minus 80 XA. And for N is what? Just 20. So now you already know N1 is 100. So you can replace the N1 with 100. So using the information of 40% or 0.40 mole fraction of N at separation outlet, this is at separator outlet. So N is 20 kilomole per hour divided by the total number of mole. 80 times 1 minus XA plus 100 minus 80 XA plus 20 equal to 0.40. So just to clarify, this is the number of mole of component N. This is a number of moles of component A and component B and component N again at the outlet. So from there, you can find out the XA because it's just one equation, one unknown, so easy. So if you do this, you get 0.9375, which is approximately equal to 0.94. I hope you get the same answer. Okay, so in summary, you should know multiple unit operation. You should be able to sketch the block diagram based on the description of the problem. Do a DOF analysis. So there are two approaches to do DOF analysis. One is to find the CV, find a control volume with UF equals to 0 and start with that control volume to find some information and then only proceed to the other control volume. So this is the most common approach, which will make your life easier. Or if you cannot do that, you need to analyze the whole flow sheet, look at all streams, how many variables you have, and how many independent equations do you have when you are desperate and have no choice, unfortunately, because such is life. Alright, so any questions, please contact me in the WhatsApp group or email me, or if anything, please just don't PM me in the WhatsApp. Okay, I hope you can do tutorial 7. So I will share with you a video on tutorial 7 and all the best.